So welcome. Let's orientate ourselves for a moment. What are we trying to do? We're trying to take some kind of rate function and retrieve back our original function. And what we've realized, or we've been told, is this is actually the area under a curve. And we started to believe this because we looked at if it was constant, if this rate function was constant, I'm sketching in the air what this graph of this function, this constant rate function would look like. And then we thought, wait, this reminds me a lot of maybe driving, right? If I'm going at a constant rate of 60 miles per hour and then go over an interval of length 3 hours, then how do I figure out how far I've gone? Well, I would take the 3 hours and multiply it by the rate. And so I would take 3 times 60 and I would get 180. Okay, I've gone 180 miles. So I would recognize that. But we looked at that earlier and we said, wait, that's also the area of that rectangle. So then we tried to go through an example using left endpoints. And we'll do, in this lecture, we're going to do the generalization of that. But what are we doing? We're taking that area through the curve. We're basically approximating it by rectangles. It's easy to find their area. And in our minds, we know, and I know for sure, that if that was a constant rate, that would have given me back my original function, how much I have actually moved. So we do this in a particular example, and now I want to kind of give you the notation for this. It can feel a little funny at first, but once you get used to it, it's actually really useful to work with, and you can actually get used to it. One of the things I might advise is if you're getting a little confused by some kind of summation, is to look at an example of it where you actually kind of write it out and see if you can correspond that in your mind to remind you of how it works. So let's go ahead and do this. So I've got I want to draw for you. So I have the graph of a function. In fact, I'm not even going to draw my second axis. I have some very squeaky pens here. And then I have my function y equals f of x. So let's go ahead and draw that. So this is going to be the graph of my function y equals f of x, which is actually my rate function. So now the other thing I look at this, it tells me I'm going to start at A and I'm going to end at B. Okay, so that's some information that I get from there. And now what I'm looking at is I've got, okay, well, let's divide this up into, oops, I wrote 5 subintervals, remembering from last time instead of putting a more general form. So I'm changing this 5 to be an n. But now you can actually see exactly how I'm changing to more general notation. N is my more general notation. Okay, so now what does that tell me I want to do? So I want to divide this up. So I'm going to call this x naught. And I need to figure out, well, how far spaced apart are these? Well, I can do the exact same thing that I did in the last portion, right? So I can take, well, how far spaced apart are they? Well, my delta x, how am I going to figure that out? Well, just like I did in the last video, I know that this length here is b minus a. And then I want n subintervals, so I want to take the whole length, b minus a, and divide it by n. So let's go ahead and do that. So I want to take b minus a and divide by my n, coming from the n subintervals. Okay, so now I think about this. So I'm going to call this x0, and then where's my next one? Well, if I think about it for a moment, and I'm going to call that one x1, where does my next little piece end up being? Well, I want these to be equally spaced, and so I want to make this so my x1 is going to equal, I'm going to take my a, and then I'm going to add to it 1 copy of my delta x, right? This is my delta x width. So I'm going to add to it 1 copy of delta x. So I just write delta x. Okay. Well, how do I figure out my x2? Again, I would start here, but now I'm going over 2 copies of delta x. Right? And then what if I keep on going? You can probably figure out this matches up now. The 2 matches the 2, the 1 matches the 1. Ah, okay, this is not so bad. I can take my... I'm going to slightly move this over. Let's say that it's like here. So I have an xj minus 1 is going to equal, again, I take my a, and then I add to it j minus 1 times delta x. Let's put an xj here. And this is going to equal, so now I have a plus j times delta x. Well, now we have to think for a moment. How do we get all the way up to b? Well, that's going to be my xn. I added up n times delta x, which you would see would cancel that, and I would actually get exactly what I want there. So this, another way to write this is that this is actually equal to xn, because it's a plus b minus a over n times n. So that works out very nicely. And now we'll just kind of draw our picture. And with a shortage of markers, we're going to do this in red. So we're going to go up until we hit the graph on the left, right? That's our height. That's f of x. I go over to the intervals and then down. So this area is A1. I keep on doing that up till I hit the graph, over, down, area A2. I'm going to keep on going. And let's do this one over here. This one goes up, over, so this one goes above it. You can see actually that actually corresponds to the fact when my function is increasing, they're below. When my function is decreasing, they're above. That's okay. And then I would have had one here from xn minus 1. Maybe I'll even stick that in here just so that you can see that would have come from the xn minus 1. Okay. And now again, we'll do this just kind of like we did before. So now I'm going to take my ln, and this n is precisely this. So how did we figure this out? So this equaled, so I want to take area 1 plus area 2 plus tuck, 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 area j plus tuck, 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 area an. And then we look at this and remind ourselves, like this point here is the point a f of a, which tells me that this height here is actually f of a, right? So then that allows me to do these areas just by doing width times height. I have a delta x, I have an f of a. So I'm going to get, and remember that this height is actually coming from the x naught there, so I'm going to write it that way for us. So this is going to equal f of x naught times delta x plus f of x1 times delta x. Okay, and then we keep on going, so tuck, 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 tuck. So if I'm doing the aj, that actually comes from this side, so that's actually xj minus 1, which is kind of consistent with what's going on here. That number is 1 less. So this is f of xj minus 1 delta x all the way up to f of xn minus 1. That's okay, delta x. Right, we don't have any rectangle that uses the height at this point, right? We only have one that uses xn minus 1. So we know that we're done there. And then this is equal to, in my sigma notation, the sum from j equals 1 2, and then we put this in red. And then we can see for each of these, we remember that we go f of x j minus 1. Just like in each of these, that number is 1 less than that number, so that's good. Okay, times my delta x, and then we know that we can bring out our delta x. So we get the sum from j equals 1 to n of f of x j minus 1. This is a very nice, oops, this should be an equal sign. This is a very nice, clean, compact way to write this all out. Okay, how I've written this here, I can do the whole thing all at once. And this is called sigma notation. So this has a very special name. It's called sigma notation. Okay, and then we kind of can write this in a nice box over here just to make sure that we picked out exactly what we're doing here, that this is equal to, so we have Ln is going to equal the sum from j equals 1 up to that n. Oops, and maybe I'll pull out the delta x. It's a cleaner way to write it, so let's give you the cleanest way to write it. So we have delta x times the sum from j equals 1 to n of x of j minus 1. Okay, so this is just the generalization of what we did before, but putting it all notationally, we can work in a more general setting. We just have to always keep this picture in our mind. If we're having a little trouble setting it up, to remember this is okay. I'm just computing areas of rectangles. The a plus j minus 1 delta x's, right? These all came from the fact, so that's another thing that I kind of want to emphasize here, is that xj, so I didn't tell you what this meant here, I showed you up there, so let's emphasize that here. So what are these? So xj is going to equal, you would have seen from over there, this is just going to equal a plus j times delta x, okay? And then my jth interval is xj minus 1 xj, okay? So we're just kind of putting this all into formal notation. That's okay. We don't get confused by that. We start out with an interval from a to b. Remember, its length is b minus a. So if I wanted to divide it into n pieces and know the length of each width of each piece, I take my entire length, which is b minus a. I divide by the number of subintervals, which is n. And that's how I get my delta x. And then how do I move over? So this would be my first interval. I moved, for its left endpoint, I moved over 0 times delta x. But to get to my next interval, I have to move over 1 times delta x. 2 times delta x, and so on. And that's how we end up having these endpoints of our intervals coming from a plus j delta x. Okay. Now, that gives me that these are my intervals. And I can actually put those, I want to find the areas of these rectangles, so I start with my width is delta x, because it's the width of my subinterval. And then my height actually comes from the graph of the function. And because the second coordinate is f of a, that gives me the height is actually my f of a. And so now I'm just adding together these rectangles to approximate the area under the curve to take me from a rate function back to my original function. And so that's kind of how the left endpoint approximation works. Why is it left endpoint? Because I go up on the left endpoint of each interval to hit my graph. So thank you, and I'll see you in the next lecture.